where you can define a Hamiltonian, but there is no correlation, there is no type of relations between the Gaussian brackets. Then can we tell that it's a Hamiltonian system or not?
Now, what's the meaning of that? I mean, you need to give me Hamilton's equations of motion. Right? You need to tell me the equations of motion are of this form. Then the symplectic structure is already there. So I tried to cast that slightly more generally by saying that given Poisson bracket relations and a scalar function, h, etc., then you have Hamilton's equations in this form. Of course, that's not how you derive things in physics. In physics, you start with the postulated Lagrangian, the variational principle, Hamilton's principle, you get the Euler-Lagrange equations, and then you eliminate, you make a Legendre transform to what's called the Hamiltonian, and you discover Hamilton's equations. Of course, you can derive Hamilton's equations from the action principle directly also. And as you know, in elementary courses, you're taught the difference between the Hamiltonian and Lagrangian formalism, and you're also told one has certain advantages and disadvantages, and the other has certain other advantages and disadvantages. For instance, at an elementary level, Lagrangian systems, the forces of constraint can be taken into account easily in Lagrangian systems. Dissipation can be taken into account fairly easily in a Lagrangian formalism. It can be generalized to the case of fields. It can be generalized to relativistic cases where the Lagrangian density is a scalar, a Lorentz scalar or something like that. On the other hand, the Hamiltonian system has its own advantages. Symmetries look much more obvious and easy, much more transparent in the Hamiltonian system. You can give physical meaning to the constants of the motion, which generates symmetry. You can quantize the system more easily in the Hamiltonian framework, and so on. So there are certain advantages and disadvantages to both. And of course, there are cases where you can't have one and you can't have both. You need to know when you have a degenerate Lagrangian, for example, or a degenerate Hamiltonian, then when the appropriate Hessian matrix is singular, you can't transform from one to the other. You can't make the Lagrangian transform. But we're not getting into intricacies of that kind. It's a special kind of dynamical system with a lot of structure to it, and it looks like classical mechanics obeys that, and there's an absolute quantum version of it. Now, more generally, we want to include dissipation and so on and so forth. We start asking a question as to what do flows in phase space generally look like? What is the general picture that one has? And that leads one naturally to a hierarchy of increasing apparent randomness in the behavior of a dynamical system. So I'm going to give informal definitions. Formal definitions are there in the textbooks and so on, via some pictures, and you'll see with examples where this leads us. So the first of these is periodic motion, of course. That's regular or periodic motion. And then quasi-periodic. That was a mild generalization of periodic motion. Next in degree of complexity comes what's called ergodicity. Again, in terms of pictures, what this means is, if you have some phase space, then if you start with a set of initial conditions here, in this little patch here, this volume element, then as time progresses, this volume element maybe evolves to that, that maybe evolves to this, and so on. And very loosely speaking, if given any point in this accessible region of phase space, you wait long enough, you will discover, if the system is ergodic, that some member of this initial patch visits arbitrarily close to that point. So, members of any initial set here, any set, come arbitrarily close to every point in a region of phase space, in this case the whole of phase space, then I'd say that the system is ergodic. If that happens, then the immediate advantage to this property is that you can replace long time averages by averages over some given distribution, static distribution in this phase space. That's what you do in equilibrium statistical mechanics when you say, look, I have a system which is very complicated, it's dynamically complex, I don't even try to worry about it. I simply say if it's isolated and it's in thermal equilibrium, then all the averages of thermodynamic large quantities are all time independent. Therefore, the probability distribution must itself be time independent. And in the absence of knowledge, in the presence of full ignorance, you say that every portion of this energy surface, every volume element, is equally probable. The system finds itself there. So it's assumed to be ergodic on the energy surface, on the hypersurface where H is constant. Now, of course, when you have special behavior, when you have exceptions to this, like periodic condition behavior and so on, then this breaks down. But in general, if the system has got enough junk in it, this is believed to be true. Further things are also believed to be true, like a little disturbance from this equilibrium state will take you back to equilibrium via what's called linear response theory, which works by the magic that the very same fluctuations that cause a departure from the typical or average value also help you to restore equilibrium. So, yeah. Yeah. Yeah, then you have to be on the intersection of both these surfaces. Yeah, it's not fully covered. What he's saying is that if you have an n-dimensional phase space, then if you have a Hamiltonian system, n degrees of freedom, then the surface on which h is equal to constant is a 2n minus 1 dimensional hypersurface. And in equilibrium statistical mechanics, you say that it's generally there. However, there are other constants of the motion. There could be the Galilean invariants, for instance. So for a given state of motion, you are in the intersection of all those surfaces, all 10 of them or whatever you like, in general. But most of the time when you do statistical mechanics, you assume a given state of motion for the system, like the total momentum is 0, the total angular momentum is 0, etc. So that those numbers are given to you already. And the only thing in which you have fluctuations would be the energy, for instance, if you put it in contact with the heat path, etc. That's the reason you assume that, after all, to make it more formal, the density operator satisfies this equation. It satisfies the Liouville equation, and if it's in equilibrium, then this is 0, so that implies that h with rho equilibrium is 0. And the normal assumption is rho equilibrium is therefore some function of h, and depends on the ensemble what function it is. However, it's actually a function of h as well as the other operators which Poisson commute with h, the other constants of the motion. So strictly speaking, you must use Lagrange multipliers for each one of those guys. But once you tell me that the motion is a given motion, all those numbers are fixed forever, then all the copies of the ensemble, that number is fixed always, then you don't have to worry about it at all. But there are significant cases where you do, as Sam was pointing out a couple of days ago. When you have black hole physics, then you do have to put in those other constants like the total angular momentum, etc. It's important that you do the ensemble. The rules will change. There will be Lagrange multipliers for those other constants of motion as well. Is that a fair statement, Sam? Is it? So you do have to, in the astrophysical context, change the ensembles and so on. You have to. Even in this equilibrium statistical mechanics, when you increase the number of particles, when that becomes free, then you've got to put a Lagrange multiplier for that, and then you have to introduce a chemical potential. So that is certainly. Okay, so now let's come back to this meaning of this ergodicity. Very loosely, this is what it means. However, this is not the most complicated possibility. What can happen is the following. And incidentally, an example of an ergodic system was the quasi-periodic system with two oscillators in commensurate frequencies that I mentioned yesterday. There, the motion occurs on a two-dimensional torus, but it's ergodic on that torus. In other words, any set of initial conditions on that torus, any patch of initial conditions, will eventually come to the neighborhood of every part of this torus. Or to put it another way, if I took the Poincaré section of it, which is what I did, the circle map, the iterates of any point would densely and uniformly cover this circle and be ergodic on this circle. Further, if you started with a little initial set of conditions and you exercise this time evolution, you wait long enough, this little element will come arbitrarily close, members of it will come arbitrarily close to every point on this surface space, on this circle here. But they do so without distortion in shape. In the quasi-periodic case, it was almost exact. This thing was just translated all the way around in this circle. But if the map is a little more complicated, then it doesn't have to do so without distortion of shape. There could be small changes of shape, but no gross violation. But the next possibility happens when you put a drop of Dettol or ink inside a beaker of water. It's a famous example, and don't stir it. Leave molecular diffusion to take over. And that little drop of water puts out, of ink puts out tendrils. and you start with something that's quite regular. After some time it looks like this, and after some time it looks like this, very stringy, etc. Even if the volume is conserved, even you know that you've got 1 cc of ink in 100 cc of water, you know there's always 1 cc of ink, assuming there's no chemical reaction going on. But that 1 cc will start spreading out, and you see all these beautiful patterns. It's completely not stirred or anything. And eventually, after a certain amount of time, you don't even see the ink anymore. It's become very dilute. But it's all there, and it's spread out, and it's got completely mixed. So the next one after ergodicity is mixing. Yeah.
Distortions of the configuration space means what?
No, not configuration space. Distortion of this volume element. Distortion in volume element. That means this point goes to that point under time evolution, but this neighboring point goes somewhere else, goes there under time evolution.
Is it needed that it has to be connected, or can it?
No, it doesn't have to be connected. It doesn't have to be connected. It could just go into separate pieces. Each goes its own way. That's it.
So it may happen some of the configurations never attend.
Pardon me?
It may happen some of the configurations never attend in this case.
Some of the configurations?
Some of the configurations never attend by the systems.
Never attend? No, that's not the point. No, I'm going to define mixing very precisely. But what you're guaranteed, absolutely guaranteed by ergodicity, by the way, mixing implies ergodicity, is that if you wait long enough, members of this initial set will visit arbitrarily close to any point in the phase space. Not all points visit all points, no. Some member will visit somewhere, some other member will visit somewhere. So members of the initial set will find themselves everywhere as you go. That's what it implies. So it's very clear that mixing implies ergodicity, but ergodicity doesn't imply mixing, because mixing also says that the shape of it could be distorted very badly. Whereas ergodicity simply says, if you have only ergodicity, it says points which are separated by a certain distance, that distance doesn't increase with time in a systematic way or anything like that. Now the next question is how far? How rapidly does it separate? How rapidly does this separate here, this point to this point? Given that they are infinitesimally further away initially, how fast does it separate? Well, you know the answer in the case of diffusion, pure diffusion. How fast does it separate? T to the half. T to the half, right? Typically distances, diffusion always says, well, that's the most important thing of all. It says r squared to the power half is proportional to t to the half. Root mean square distance is equal to the square root. This is the central limit theorem in operation here. So it simply says that if I walk purposefully in a given direction at constant speed, the distance is proportional to the time. But if I do so randomly, without any aim at all, then my end-to-end distance is of the order of square root of t. It takes me 4 times as long to go twice as far on a normal system. Normal, not on some exotic object like a fractal, but on some ordinary Euclidean space or normal space. Okay, so this goes like root of t. Of course, it's not very fast. It's extremely slow. It's still there, but it's extremely slow. And to give an example, if, for example, you waited for molecular diffusion for perfume to take effect, then the perfume industry would go broke, because you can compute from Einstein's theory of Brownian motion how fast this molecular diffusion happens, and with normal viscosity, with still air, with room temperature, etc. If a very attractive person, I want to be gender neutral here, comes to the other end of the room, which is number 5, it will take me about a month to sense it. The whole purpose is lost. On the other hand, there are thermal currents and there's advection, which helps. So if you switch on the fan, it's much more effective. Therefore, now you can see it's driven diffusion. It's driven, and then if you have turbulent diffusion, like you have in clouds and so on, then it goes much faster. And you must have heard of certain cases of it, superballistic motion, etc. So all possibilities exist. On the other hand, this mixing I should like to define a little more formally. There are many, many kinds of mixing. There's something called strong mixing, there's something called weak mixing. So here's what strong mixing is. It's also called exactness in the literature. It says, given a phase space whose total volume is omega, measures is omega. Yeah.
So for mixing you need external perturbation?
No, I don't need external perturbation. That's the whole point. You don't need the system does it all by itself, provided the time evolution is sufficiently complicated. That's what we're going to show. In that example I gave, yes, certainly that's true, you need to have. But if there are thermal currents, for example, this will do it in normal air. But on the other hand, for dynamical systems, the time evolution itself does it. Yeah. Right? Why not? Things can separate exponentially just by time evolution. Look at x dot equal to x on a line. Here's 0. This is the x-axis. An initial point x naught, after some time t, finds itself at x naught e to the power t. An initial point x naught plus epsilon finds itself at a point which is x naught e to the t plus epsilon e to the t. So this separation is exponentially larger than that separation. The system has done it all by itself. That's not chaos. This is not chaos. Just that you have a lot of room and it's just exercising its freedom to be there. Chaos is much more subtle than that. It will be in a bounded space, as we see. So what is strong mixing? Well, very roughly, it's the following. It's exactly this rum and cola analogy that's given, or whiskey and water analogy that's given in the textbooks. You put a certain amount of whiskey in water or rum and cola, and you stir it, then after a while it becomes uniformly concentrated everywhere else. And the way they write it formally is to say, suppose you have a certain initial measure, a volume element in phase space of the stuff that you want to mix, and this set is A, and as time evolves, it changes in some complicated fashion. So after some time it becomes this, and then it becomes this, etc. This set of initial conditions. Let's suppose that the measure of this full phase space is mu of omega, volume. Say, I could set it to be 1, take it to be mu of omega. And this A has a measure, mu of A. We will talk about measures subsequently, invariant measures. But for the moment, imagine it's just a volume element. Then, after, and let's look at it in discrete time steps. So this is A at time 0, and then this is A at time 1, so A1, and then this is A at time 2, and so on. After time n, it's A sub n. Then look at a reference window. Look at some volume here, sub-volume, which is your reference window, and let's call that D. If the thing is completely stirred, then what would be the amount of A that's inside B? That has a measure mu, which is A to the power An intersection with B. That's the amount of, after n iterations, this is A, this is An, and this is the amount of it that's inside B, intersection of this. And there is as much of it inside B, in B, the ratio, as there is A itself in the entire volume. This means it is uniformly mixed, same percentage, in the limit as n tends to infinity. If this is true for every set, measurable set A and every measurable set B, then we said it is said the system is said to be strongly mixing. Strong mixing implies ergodicity. Even weaker forms of mixing imply ergodicity, but this is really strong. Really strong. It says the system is thoroughly mixed up for any A and any B. There are other weaker forms of mixing. For instance, just to give you one of them, this is called strong mixing. A form of weak mixing would be to say, all right, take the measure of mu, A intersection, the time evolution operator run backwards, T n K with B, subtract from it the measure of A, the measure of B, take the modulus of it, and take the Cesaro sum of this, which is K equal to 0 to n, 1 over n, and take the limit of it as n tends to. If this is equal to 0, if this is so, then you have what's called weak mixing. Weak mixing does not imply strong mixing. Strong mixing implies weak mixing as well. etc. And there are many other ways of defining mixing. But we are going to use a very intuitive approach, and I'm going to assume that the systems we are going to look at, and we'll see explicitly, are strongly mixing. Yeah.
In the same way, can we find between ergodicity and
Yeah, sure you can. Ergodicity, yes. There's no, yes you can. I leave that to you as an exercise. Yes. What's the corresponding statement in case of ergodicity alone, but no mixing? So an easy way to do this is to look at some examples and then try to work backwards to write it in this form of measure theoretic language. So I'll leave that as an exercise.
These both are integrable systems, right?
No, no. I'm not saying anything about integrability. I'm not saying anything about integrability at all. If the system is integrable, then in general it's not ergodic. Because you can see for a Hamiltonian system, if it's integrable, for the kind of system we looked at, it is not ergodic in phase space at all. The motion for any set of initial conditions has restricted itself to an n-dimensional torus in a 2n-dimensional phase space. So certainly those trajectories are not wandering around at all. Certainly not mixing or ergodic.
but you can still say that ergodic in action and contours. That
Well, in the sense that a simple harmonic oscillator is ergodic on its phase trajectory. That doesn't do much for me. Right? It's a whole of phase space and is on a line. Of course it covers that. So it's not doing better. Or on some torus. The question is what happens when you get rid of it, and then what happens to initial conditions? Is it uniformly mixing everywhere, uniformly ergodic? And that will come back to Hamiltonian systems that happens only after you have what's called global stochastic chaos. Till then there are regions of phase space which will never wander out to live near where they are. But I have in mind some very general statement here, nothing to do with Hamiltonian systems, very general. The next in complexity is the following, after mixing. So mixing implies ergodicity, but this is not implied, not true. Strong mixing definitely implies ergodicity. The portions of this are there everywhere.
Yeah.
Whatever BB is there. I don't care, I'm only saying that some member of this initial set will come arbitrarily close to every other point. This measure is not zero. Whatever be the set B, it's not zero. So clearly this is so. Yeah. What's that? Okay. This is the time evolution operator. So the set A goes to the set TA, goes to the set T squared A, etc. It's a time evolution operator written in abstract form. That's the rigorous way of writing it. I could invert it backwards. So you see, the reason for doing this is because when things are diverging exponentially, you have to be careful mathematically. Therefore, you run time backwards and say it came from a convergent state. So the mathematicians like to do that. Yeah. Pardon?
that window reference window
Is fixed. Any window.
So you don't need to operate that beyond it. You can make
Well, I've gone backwards, right? This is loosely speaking the same as T to the Ka intersection would be. On this. This is to make sure that I'm not looking at things which diverge out of control, but which shrink backwards.
The right side, the strength of the mixing. So what is the value of minimum?
Okay,
Of the maximum?
for each kind of mixing, I can define what's called a strength of mixing. I'm not doing that as yet because I'm going to define my mixing, and the case I'm interested in is when there will be exponentially fast divergence. And then I will define the strength in terms of the Lyapunov exponents. Yeah.
So what is the measure? Is it the volume that is...
Think of it at the moment as volume.
So then, in the case of strong mixing, you start off with a small volume and then that volume should become equal to the phase space volume.
Why?
Because
No,
it's-
take the Hamiltonian system.
Oh, the volume is conserved.
Yeah, volume is conserved. Total volume is conserved. Volume of every element is conserved. These are all measure preserving flows. If the flow is not measure preserving, I got to be damn careful here. You could ask, suppose a whole volume element in phase space shrinks to a point or shrinks to a line whose volume is zero, it's still there, but the volume is zero. What happens then? You have a ball that becomes a line, a string. What happens then? No, I have to be very careful then. Then I will wait till asymptotopia is reached, till the system has settled down to some attractor and define a measure on that attractor appropriately. So I didn't want to introduce that complexity right away. I just wanted to give you this milk and water or whatever analogy in the beginning, but afterwards we will look at.
Still Hamiltonian systems.
No, I'm not thinking of Hamiltonian systems at all.
We are taking the arbitrary system.
Yeah.
The volume could actually stretch into whatever.
If the volume becomes infinite, then I'm in trouble and I'm not going to be interested in such systems. Always I will look at systems where the volume is bounded in phase space. Because if it becomes infinite, I can have trivial divergences, like that x dot equal to x example I gave. Things will diverge exponentially because there's a lot of infinite room. I'm not interested in that. What I'm interested in, to put it in a nutshell, is the system goes away, but the phase space is bounded, so it comes back, is bounded, comes back, and I have mixing, so that I lose information. And we'll carefully quantify this loss of information when I define the Lyapunov exponent.
Some power of n, it's a function of mu rather than mu a after some n iterations.
Yes.
So it could also be a function of some bounded function of.
You mean this measure?
I'm saying that after n iterations,
Uh-huh.
that measure a intersection b
Uh-huh.
would be equal to.
This would be a function of n, of time, which is n. Definitely, it is a function, but I'm saying in the limit, after you stir it fully, then everything is uniform constant. That's all it says. I don't know.
So it's expected some quantitative limit of the strong mixing. So
Yes.
one can say that the system is in ergodicity, following ergodicity.
No, the system
It is
mixing
expected.
already implies ergodicity.
Okay.
There's no way in which that measure can be non-zero unless parts of the initial set go and fill up everywhere. Mixing implies ergodicity, but ergodicity doesn't imply mixing because mixing also means that you have stretching and folding, whereas ergodicity doesn't have that. It was believed for a long time that equilibrium statistical mechanics required the ergodic hypothesis, that things were ergodic on the energy surface. People spent a lot of time trying to prove it. But it turns out to be too restrictive a condition. It's too restrictive. You could have mixing and you still have equilibration. So today it's believed that if any system is sufficiently strongly dynamically mixing, then the fundamental postulate of equilibrium statistical mechanics is valid. That's what.
Implies ergodicity, right?
Pardon me?
Mixing.
Mixing implies ergodicity. Ergodicity does not imply mixing. So think of it as mixing means the shape also changes, ergodicity means things are going around but shape doesn't change.
Sir, and if you have a measure non-preserving flow,
Yeah.
these things will not be, the limit may not be defined actually.
That's exactly what I said. So you will now wait till asymptotopia is reached and then talk about the measure of relevance to us. And I'll define a measure on the attracting set, finally, which need not be the volume of phase space. So I'll wait till that happens and then take the limit. Okay. All right. So now the question is, how fast should these things separate? And the answer is, there is a very basic difference between a separation according to a power law, like t to the half or t to the 1 or t to the 20,000, versus exponential separation. Because exponential separation makes the future uncomputable. If there is amplification of error exponentially, then you cannot compute anything meaningful. On the other hand, if it's any power law, you can still compute things in polynomial time. So physicists make a very big difference between sensitivity to initial conditions, two initial points separating in time as a function of time. This separation, if it's a power of this initial separation, high power, mathematicians would still say it's very sensitive to initial conditions. On the other hand, physicists would say extreme sensitivity to initial conditions if this is exponential. And that's the generic case that happens in physics, in problems. Most dynamical systems, there is at least one direction in which this separation is exponential. In the gas in this room, for instance, in the phase space, the exponential separation in phase space trajectories of two initial points in phase space is extremely rapid, and the largest separation is an exponent which is proportional to the number of degrees of freedom of gas. So that exponent itself is 10 to the power 23. And the separation happens like e to the 10 to the 23 times t. So that it's completely hopeless.
So you're talking about that today's for equilibrium statistical mechanics.
Yeah.
Ergodicity is not so basic possible lights, if
Yeah.
there is no mixing type.
Yeah.
So, ergodicity, that means ergodicity may break in some equilibrium stresses.
No, I'm not going to talk about phase transitions and the breaking of ergodicity and so on. So, the breaking of ergodicity is what freezes you to certain portions of phase space. And of course, once that is broken, the system still mixes only in that region of phase space. It doesn't go everywhere else. What does broken ergodicity mean, or what does a phase transition mean? It means that there is a huge infinite barrier in the thermodynamic limit to the other phases, which cannot be restored by fluctuations alone. So that's why